So I have a sample problem on the board. I give you a function. It's a cubic. All right. I don't exactly know what it looks like. You know, I don't know if it has a couple peaks in it. I don't know if it does this. I'm not, you know, it doesn't matter. But it's a cubic. It's a polynomial, so it's defined for all reals. All right. And I'm asking you, prove a root exists between -1 of x and 1 of x. And in between it crosses the x-axis. This is an IVT problem, intermediate value theorem. And there are rules we have to do first. The first rule you have to say, if you're going to use IVT, so use IVT. If you want to pause the video and try, you should. Because this would be a classic test problem. First thing I say is f of x is continuous. You really do. You have to say it's continuous. You have to somewhere say this. And the reason, how about because it's a polynomial? That's enough of a reason. We know by function types that polynomials, roots, trigs, and rationals are continuous in their domain. Polynomials are defined for all reals, thus that you don't have to even worry about it. You don't have to define that it's continuous in there. There's no vertical asymptotes on a polynomial. So I just say f of x is continuous because it's a polynomial. Next thing I got to show is that f of a and f of b are not the same. And if you recall, when I say stuff like this, we are trying to prove, and I suppose I could do it more in this, I can make the graph a little bit more like our situation. A, B, where you're going to find, I think this is negative and this one was positive, and we wanted to prove that somewhere there's a root. Okay? For this to happen, we have to show that f of a and f of b are not the same value. Alright? So I would go f of -1 equals and f of 1 equals. And when I do that, I get -1 plus 3 is 2. 2 minus 5 is answer. You get -4. You plug in 1 and I get 8. So f of 1 does not equal f of -1. You probably wouldn't have to put that, but I'll put that note in there. So that's the second thing we have to show. All right, so we've shown it's continuous. All right, we've shown that the f of a and f of b are not the same. So guess what? We now know that there exists a number n, and I'm going to write this in a paragraph next, but I'm going to do it as statements first, that n exists between f of -1 and 1 such that c exists between a and b, right? Or this would be f of a, I should probably do this in general terms first, f of a and f of b. Well, this time what we're trying to prove is a root. A root is 0. Is 0 between -4 and 8? Absolutely. So somewhere between, so we know now this exists. Now we just got to say, hey, why do we know? Okay? So we did this red. Let's go to a different color. So now we got, because you wouldn't have to put the red on a test question, but you'd have to put on a test question something like this. And again, it's annoying sometimes to be my students, right? Because I am not ever saying this the same way twice. You can't memorize it. Or if you do, you got to pick one of the times I say it, and then I say it differently the next time. I usually start by IVT, I think, though, usually. By IVT, since f of x is continuous, and f of -1 does not equal f of 1. And, actually, I'm going to use the notation this time. F of -1 is less than or equal to 0. Is less than or equal to f of 1. You guys agree? That 0 is between -4 and 8. Now, you could put -4 and 8 there. I know, Megan, you did that. That's fine. Then C exists such that C is between those values, right? And f of c equals what? How about 0 this time, right? We're proving the root. It's just between the
Hey, where you put like the -1 and 1 to c, like, would you use like the -4 and 8 instead?
No, because the -4 and the 8 are the y values right here. Right? and the C is the X values, right? And again,
That makes more sense.
do you understand now? And I'll circle the graph there, and I'm going to blow that up so people on the video can see it. So again, when you're talking about the C, we'll get this nice and big, get this down. The C is between, I'll do it in red, the C is between A and B. The N is, well, in this time, N is 0, but I'm going to put N up here so it's more obvious. And N is between F of A and F of B. So N is the Y value, C is the X value. And again, you know what? I don't care what letters you pick. Everybody uses N and C that I've ever seen. But to me, it's more important that we have this understanding. And again, we're going to use this on like cars taking left turns, cars taking right turns, you know, functions that we know are continuous. All right, I'm going to pause the video, put up one more, and then we're going to take some homework questions today. So on the next problem, I give you a function, it's piecewise. I want you to prove it's continuous or not continuous, not using a graph. We'll use a graph at the bitter end, double check. If you need a graph to get a feel for it, then you can do it, but I don't, what I would grade on this is whatever you write to show it's not a graph. But it's not continuous, or it is continuous. No graph. Alright, so if we're going to start this function, you're going to prove this without a graph, and I'm going to do the graph last. Alright, I am going to do a graph so you can see it, but I'm going to do the graph last. I'm going to prove it's continuous. What you have to realize is that we know a rule about limits. If we have a continuous function, the limit here is equal to the value of the function. It's a special situation. You know what I mean? And you think about this. If I graph a removable, this is untrue. Do you guys agree? If I graph a jump, this is obviously untrue. If I graph an infinite, it's undefined, right? So all the removables fail this basic test. So if you want to prove that a function is continuous, you have to show the blue. In green, I have to then say, well, not only do I have to show that, I can show it everywhere. But when you look at the pieces of this piecewise function, line, parabola, line. Guys, these are all polynomials. So these functions are continuous everywhere. So when we have this situation, you can write a note. Pieces are continuous everywhere in their domain, right? And I wouldn't even make you do this, okay, actually. But we know this. So all we have to check is what? We just have to check these overlap points. And if I want there to be a limit, I have to have a left hand and a right hand and the value of the function. And that will prove continuous or not continuous in each step. So what I'll do is I'll make a column for x equals 0, and I will make a column for x equals 1. And I'm going to take the limit as x approaches 0 from the left-hand side of the function. I'm going to take the limit as x approaches 0 from the right-hand side of the function. And I'm going to compare that to f of 0. If those three outputs are the same, guess what we know? We know it is continuous. It will match this rule for the two left and right hand, and it will show that that is the same as that. The easiest thing is to do, I'm going to work upside down. I'm going to work from the bottom up. Yeah, wrong page. So f of 0, if I plug 0 in, it means use this function here. 2 times 0 squared is 0. All right? I don't need all this extra stuff in there. All right, so then I go from the left side. The left side is the lower side. It's this side, right? So I want to plug 0 in there, and boom, guess what I've just proven? It's not continuous. I can stop now. I'll do the right side, see if there's a limit. I do the right side, it's there. So there is a jump here, guys. Do you see the jump? So not continuous at 0. Right? Boom. And I don't have to write anything because I showed it right here. Alright? Now I'll do x equals 1. I probably should do this maybe in a different color. We'll do blue. So I'm going to do the limit as x approaches 1 from the negative. I'm going to do the limit as x approaches 1 from the positive. I'm going to do f of 1 of the function. And you notice I write out all the stinking notation, right? You guys love notation, so do I. So I go to 1 negative, which is the parabola. Negative 1 squared is 1 times 2 is 2. Alright, I'm using now I'm going to go to the other function. I plug in 1. 2 minus 1 is 1. And again, I can stop now. I have another jump, right, guys? I got another jump. And f of 1 is 2. Now, the awesome part of this, now that I have this information, I can do the graph really fast. Alright? 1, 1, 2. Alright? F of 0 is 0, I'll put that point right there. F of 1 is 2, I'll put that point right there. I just read this value and this value. Okay? Going into 0, it is 2. Open circle in. Oh, and I know it's a line. I should might make it right. I know it's a positive slope line, so it must look like something like that. In between, it's a parabola, so it must look like that. And then the positive side of 1, alright, the positive side of 1, it's 1, and it's a line again. And you notice I didn't even look at the functions outside of general field as a line, positively sloping, negative sloping with a parabola. And that's the graph. And obviously you can see when you make the graph, it's not continuous. So it's not continuous at 1 either. And I proved it. I proved it. I proved it with this. I proved it with this. But you have to do that, you got to have that understanding at the very tip top. Alright, are the 3 pieces themselves continuous in their domain? The answer is yes. And this is how you prove a function is continuous or not continuous. Alright? You show the left hand, the right hand, and the value. Would you like to see one that is continuous real fast? Sure. Then we'll take questions. If I want, I'll make one that's continuous. I'll have to think just for a second. We'll make it let's put 1 spot in. Oh. Alright, I know that's kind of lame, but it works. It's a line and a parabola, and you probably can see right away if you can picture the graph in your head. But as you look from the negative, and I'm going to write out where I'm putting 0. I'm putting 0 in this equation. When I look from the positive, and again, I'm going to show which function I'm putting it in so we all understand where they're coming from. Oh, it's all g of 1, isn't it? Changing that. This is a continuous function. The limit exists, so I can now write, if I want to prove it, it's continuous. Why? Because the limit as x approaches 0, the right hand and left hand are equal, equals f of 1. You guys agree? It's continuous. Boom. It's continuous for that reason. If I want to make a graph, just to end it, it all ended at 0, 1. You guys agree? Boom. That was a line to the left, parabola to the right. And again, all our stinking labels. And again, proving continuity is understanding how limits in the functions work. Alright, I'm going to stop and record this. We'll do some homework